Hello everyone, welcome to Basics e-learning.
In lesson number 3 video of Z transform video series, I am going to discuss properties of Z transforms. Lesson number 1 and 2 videos I am going to leave the link in description box. In my previous video series, that is Introduction to Signals and Systems, which covers almost module 1 completely irrespective of the university to which the student may belong to. So that link also I am going to leave in the description box. Please check it out. In my previous video, I have discussed the definition of Z transform and how to apply a Z transform on a given x of n. So without using any formula, directly by the definition of Z transform, one can obtain the Z transform sequences including the ROC, right? So now these are the properties that gives us the additional advantage in obtaining the Z transform of various operations on different sequences. Like whose transforms are already known. So if you know these transforms, then you can apply on the given sequence. These properties you can apply on the given sequence to find out the Z transforms in an easier way. So these are the properties that I am going to discuss in this video. Linearity, time shift or translation, multiplication by an exponential, multiplication by a ramp, time domain convolution, time reversal, Z domain convolution. Other than these, we have two more important properties. So they are initial value theorem and final value theorem. So those two theorems that I am going to discuss in the next video. Coming to linearity property, see this linearity property already I have explained in general. So now coming to this Z transform specifically, what is this linearity property we'll see. So by definition, linearity means the weighted sum of inputs is equal to the weighted sum of your transformed output. So let us see. I am taking two sequences x1 of n and x2 of n whose Z transforms are x1 of z and x2 of z. So let us write here Z transform of x1 of n is equal to x1 of z. You know, by definition of Z transform, it is nothing but sigma n is running from minus infinity to infinity, x1 of n z power minus n. Similarly, Z transform of x2 of n is equal to, we are calling it as x2 of z. That is by definition, you can write it as n is running from minus infinity to infinity, x2 of n z power minus n. So this linearity property says the weighted sum of inputs, I am taking a x1 of n plus b x2 of n is equal to the weighted sum of your transformed outputs. So a x1 of z plus b x2 of z. This is the definition for the linearity. Let us see the proof, how it goes. So proof part. See here, Z transform of x1 of n, I have written as Z transform of x1 of n as, by definition, I have written as sigma n is running from minus infinity to infinity, x1 of n z power minus n. Means in place of whatever the transform, the signal I am taking, that is coming here in here, right? So x1 of n. See here, for x2 of n I am writing. So here it is coming as x2 of n. Now, suppose if you want to write for this, in place of x1 of n, I have this much. This is my new signal. That is a1 x1 of n plus b2 x2 of n. So, in place of x1 of n, I have to write this much signal, right? So, let us write a x1 of n plus b x2 of n. That is, I am applying formula, Z transform formula. This can be written as sigma. N is running from minus infinity to infinity. This in place of x1 of n, you write this full thing. That is a x1 of n plus b x2 of n multiplied by z power minus n. That is as usual you can write. Now, this is can be simplified. This a can be written outside because it's a constant, right? So sigma n is running from minus infinity to infinity. X1 of n z bar minus n plus b. B is also constant. That is nothing to do with the summation. So n is running from minus infinity to infinity. X2 of n z bar minus n. Now if you see here, Z transform of x1 of n is defined as sigma n is running from minus infinity to infinity x1 of n z bar minus n. See, this is nothing but this one, right? So let us call this as otherwise equation 1 and equation 2. Now this is of the form equation 1 and this is of the form that equation 2. Now you can replace here. That is A in place of this one. This is nothing but the formula, right? So Z transform of x1 of Z. That can be written as x1 of Z plus B x2 of Z. So this is nothing but your linearity property. What is the property saying? That is what we got, right? So now coming to ROC. ROC is nothing but the intersection of these two signals. That means ROC of x1 of z, that is x of z, x1 of z, intersection ROC of x2 of z. That will be your common ROC of the combined signal. So this is all about the linearity property and the proof also. This is like very easily the student can understand with this proof and explanation here. Time shift or translation property. A shift in time domain signal makes what type of difference in your Z domain signal? That is given by your time shift signal. So let us see here. Suppose say the signal I am considering is x of n. So for that the Z transform of that x of n is x of z. So you know by definition you can expand this as n is running from minus infinity to infinity x of n z bar minus n. Right now suppose this x of n is shifted maybe towards your left side or right side. Suppose say this is my signal, say extended from 2 to 3. Now the same signal I have just shifted from 3 to 4. This is what is that meaning of time shift. This is n, no? Right? N. This is x of n. So it is shifted from x of n, right? So if it is shifted on the time scale, what type of change you can observe in z domain? That we'll see. Suppose say this signal is shifted by n naught times x of n minus n naught, then your z transformed signal will be z bar minus n naught x of z. Let us see the proof. So coming to the proof part. Now in place of x of n, I have x of n minus n naught. So write it. Z transform of x of n minus n naught. I am just applying the definition. So in place of x of n, I have this much. So write it down. Sigma n is running from minus infinity to infinity. X of n minus n naught z bar minus n. Now let us call n minus n naught as m. Right? Let us call n minus n naught as m. Now I am trying to change the limits also, as here n tends to minus infinity, then m also tends to minus infinity. Right? If n tends to plus infinity, m also tends to plus infinity. Right? Now this will become sigma. In place of n, I am writing m is running from minus infinity to infinity. X of n minus n naught is nothing but m. So x of m z bar minus n. See here n is nothing but m plus n naught. Right. So minus n means minus of m plus n naught. Right. I am trying to bring this in the form of definition of Z transform. So write it sigma. M is running from minus infinity to infinity. X of m z bar minus m multiplied by z bar minus n naught. I am just splitting this one. So see here, this is nothing but your Z transform definition. Instead of n, I have m constant. That's it, right? So this is nothing but x of z. So this is equal to z bar minus n naught x of z. Right? So this is proved. coming to ROC, the ROC of the shifted signal is nothing but the ROC of the signal itself. ROC of x of z is equal to the ROC of your time shifted signal. So a shift in time domain makes a shift in your frequency domain or in z domain by z power minus n naught times. So your x of z is multiplied by z power minus n naught in translation or time shift property. Suppose say instead of x of n minus n naught, if it is a plus shift, that is x of n plus n naught, then your property becomes z power n naught multiplied by x of z. So this is also a very simple property with the proof here. Next is multiplication by an exponential. So if you multiply a discrete time signal in time domain by an exponential signal, what happens to the signal in z domain? What type of change is going to happen to the same signal to the transformed z domain signal? So that is given by this property, multiplication by an exponential. So let us see. Suppose say I am taking the signal as x of n. So the z transform of the signal x of n, z of x of n is given by x of z. So as usual I am writing the definition. N is running from minus infinity to infinity, x of n z power minus n. Now the same signal x of n on the time domain, if you multiply by an exponential, that is a power n multiplied by x of n, then what happens to your z domain signal? The z domain signal will become z of x of z by a. Right? So now we'll see how it is done, the proof part. Very easy. So again in the same way, apply the z transform definition on the signal a power n x of n. Now I am considering a power n x of n as one signal. That is, in place of x of n I have a power n x of n. So now write down the formula. N is running from minus infinity to infinity. In place of x of n I have a power n z x of n multiplied by z power minus n. Right? So now see here, actually this has to be of the form a power n x power minus n, but the signal is a power n x of n. So I am writing a power n x of n z power minus n, but according to the definition of z transform, it has to be x of n z power minus n. See, now this one we have to convert into that form, right? So now let us see here. Both a power n and z power minus n are the powers of n only. So I am writing n is running from minus infinity to infinity, x of n here, a power n z power minus n. No? Can I write this as z by a whole power minus n? See here, a power n, we are writing it as 1 by a whole power minus n, right? So this is nothing but now z by a whole power minus n. Now, if you compare these two expressions, if you have z power minus n, I am writing x of z. But here I have z by a whole power minus n. Means this is nothing but z trans x of z by a. Right? In place of z, I have z by a. So here in place of z, I am replacing that as z by a. So this is how the proof is done for the multiplication by an exponential. Now coming to the ROC part, ROC of the signal, that is the transform of a power n x of n, is nothing but z by a for rx minus 1 and rx plus 1. That is, if the ROC of x of n is in the limits rx minus 2 rx plus, then the z transformed ROC will be z by a will be in this range. The lower limit and upper limit, if applied for z here, the same lower and upper limits are applied for z by a. Means your z will be a times your lower limit then to a times your upper limit. Right? So that is how the ROC of the signal is defined. Next property is multiplication by a ramp signal. So if you are considering x of n as your discrete time signal, z transform of x of n can be written as x of z, and by definition I am expanding this as sigma n is running from minus infinity to infinity x of n z power minus n. Now if you multiply the input signal, that is x of n, by a ramp signal, so the ramp signal r of n is represented as n, right? That is, if n is equal to 1, 0, r of n is equal to 0, 1, 1, 2, 2, like this. So this is your ramp signal, right? So this is r of n and this is n. So r of n is nothing but n. So now if you multiply this x of n by n, what happens? Let us see. N into x of n, then the z transform of the signal n into x of n is given by minus z into dx of z divided by dz. Let us see how this is done. The proof part we'll see. Let us go that. So now we know x of z is what here? Sigma n is running from minus infinity to infinity, x of n z power minus n. Take the differentiation on both the sides with respect to z. So dx of z by dz is equal to sigma n is running from minus infinity to infinity, x of n. See here, d by dz of z power minus n. So this can be written as, you know, d by dx of x power n is n into x power n minus 1. So this will be minus n. Sigma n is running from minus infinity to infinity, x of n, right? This minus n I am writing this side, outside that sigma part, then z power minus n minus 1. So this can be written as minus n into sigma n is running from minus infinity to infinity, x of n z power minus n divided by z. Right, now you bring that z to the other side, right? So that is towards the LHS side. Then it becomes z into dx of z by dz is equal to, that minus also I am bringing this minus. So this can be written as n is running from minus infinity to infinity. N is like you have to write within that sigma only, because sigma is that n only, right? So running with n only, so that I am writing n into x of n z power minus n. So in place of x of n, I have n into x of n. So this is nothing but z transform of n into x of n. So hence it is proved here. So if you multiply a signal, input signal x of n by the ramp, then the z transform of the signal n into x of n is given by minus z into dx of z by dz. So the derivation here is also very simple here. So take x of z and differentiate it both the sides with respect to dz. Now you can simplify. Let us see time domain convolution. Means the convolution in time domain, how it becomes in frequency domain or z domain, right? So let us take two signals x of n and y of n. The convolution of x of n and y of n by definition given by sigma k is running from minus infinity to infinity, x of k, y of n minus k, right? Now if you take z transform of this signal, z transform of x of n convolution y of n, then that signal is equal to multiplication, that is x of z multiplied by y of z, means the convolution in time domain goes to multiplication in frequency domain. Let us see how it is. So coming to the proof part. So we know z transform of x of n is by definition sigma n is running from minus infinity to infinity, x of n z power minus n, right? Now I am writing z transform of x of n convolution y of n. In place of x of n, now I have x of n convolution y of n. Now this is sigma n is running from minus infinity to infinity. I am writing x of n convolution y of n multiplied by z power minus n. But what is the definition of x of n convolution y of n? Sigma k is running from minus infinity to infinity, x of k, y of n minus k. So just I am substituting that. N is running from minus infinity to infinity. Sigma k is running from minus infinity to infinity. X of k, y of n minus k, right? Z bar minus n here, right? Now, let us change the order of convolution here like this. Suppose say, take n minus k as m, right? If you take n minus k as m here, now what happens? Here the limits are, I am writing this as sigma. K is running from minus infinity to infinity. For k, what are the terms that are involved? X of k, right? So this z bar n will become m plus k now, right? So I am writing here y of, this also you write, sigma n is running from minus infinity to infinity, right? If n minus k is equal to m here, right? N is running from minus infinity to infinity, k is running from minus infinity to infinity, x of k, and then what is this? Y of m, n minus k is m. Z bar in place of minus n, it will come as minus of m plus k. Now you change the order of integration from n to m, right? So as I am taking n minus k is equal to m, as n tends to minus infinity, m also tends to minus infinity. If m tends to plus infinity, n tends to plus infinity, m also tends to plus infinity. So here instead of n you can take it as m. I have changed that n to m in terms of m I am writing. Now this can be simplified as I am writing k terms one side. Sigma k is running from minus infinity to infinity, right? X of k, see this one, z bar minus m plus k. This can be written as z bar minus m multiplied by z bar minus k. So write it, z bar minus k, right? Then m terms you write. Sigma m is running from minus infinity to infinity. Y of m z bar minus m, right? So now you can observe one thing. See, the first term is in the form of your definition. X of z transform of x of n definition, right? Instead of n, I have k. Sigma k is running from minus infinity to infinity. X of k z bar minus k multiplied by, again, see, second term, sigma m is running from minus infinity to infinity, y of m z bar minus m. Again, this is also z transform definition. So this is the z transform of x of n, and this is the z transform of x of y of n. So this is nothing but x of z multiplied by y of z, right? So this is how this is derived. Coming to the region of convergence of the convoluted signal is nothing but the x of n ROC of x of z intersection ROC of y of z. So this is how the ROC of your convoluted signal is defined here. Next is time reversal property. So for a signal x of n, the z transform of that x of n signal is given by x of z. By definition, it can be expanded as n is running from minus infinity to infinity, x of n z bar minus n. Now, if this x of n is time reversed, see, suppose say this is my x of n. Reversed means x of minus n to the other side, right? So if you are reversing the signal, then what happens to your Z transformed signal? If you transfer the signal in time domain, from time domain to frequency domain or Z domain, what happens to that type of signal we will see. So this is again most frequently asked property. So Z transform of x of minus n is given by x of 1 by z. Let us see the property here. So we know the property I am writing. So Z transform of x of minus n, by definition I am going. So instead of x of n, I have x of minus n. So I am writing that only. Sigma n is running from minus infinity to infinity. In place of x of n, I am writing x of minus n z bar minus n, right? So but we need x of n z bar minus n format, no? So let us take that minus n as some L, right? Then if n tends to minus infinity, then what happens to L? L tends to plus infinity, because this is minus n is equal to L. Then if n tends to plus infinity, L tends to minus infinity. This can be written as, in terms of L I am writing. So L is running from now plus infinity to minus infinity. X of minus n. Minus is I have assumed it as L. So x of L, z power L. Right? So now this I can write it as, by changing the order of integration here. L is running from minus infinity to infinity. X of L. This I am writing z power minus 1 whole power L. Minus L. Right? So minus 1 into minus L is nothing but L. Now this is, see again, this is in the basic definition form. L is running from minus infinity to infinity, x of L, z power minus L. But instead of z power minus L, I have z power minus 1 whole power minus L. So this is nothing but now x of z power minus 1. If you have z here, I would have written it as x of z. But I have z inverse, so I am writing x of z inverse, which is nothing but x of 1 by z here. So this is the z domain conversion of time reversed signal x of n.
For more videos, please do like, share, subscribe to our channel. Let us know your suggestions and queries in the comment box. Thank you.